Hey guys, welcome to the video. So in this video, I want to talk about just 2 points mainly, but through and they may not seem relevant also, not strictly relevant in any case, but through these 2 points, I would like to illustrate, let's say, the limits of physics. Although if I claim that I would be illustrating the limits of physics in 2 points, that would be an overstatement definitely. So what I would like to do is that, if I'm being brutally honest with you guys, I just had these two ideas, and I just thought of sharing this with you. That's all, nothing more than that. But still, I think this would be important. They would, especially to those of you who would like to pursue physics, or not just pursue physics, but who would like to think more about physics, or like not just study it as a subject, but learn how to think like a physicist. Again, that's not really true, because I'm pretty sure conventional physicists, only very few of them do think like this. But yeah, I believe whatever you're studying, be it physics, be it something else, be it whatever, uh, spending a lot of time about the limits is very important. And by limits, I don't mean the obvious ones. Of course, every people who study physics, they know the limits of physics. We have a lot of assumptions. We assume we can neglect air resistance, we assume we can neglect that, we approximate a large system to n tends to infinite. But those are the standard limits of physics, and like those are the assumptions, which are definitely limitations. Of course, they're limitations of physics, but it's no point criticizing them, because there is no other way we could have made progress. If you are not ready to make those assumptions, make those approximations, you are stuck. There is no physics technically, and even after those approximations, you can get some very good results. So it's not a good idea, I think, to question those approximations. It's always a good idea. I mean, it's very important to keep them in mind. What are the approximations, what are the limits, what are the assumptions under which this theory, this model stands. But that doesn't mean we should just question those approximations, just for the sake of questioning it. By limits of physics, I don't mean that. I mean something a little more fundamental, something which is common to all of physics, no matter what branch of, maybe this is common to all of science actually, not just physics, but it's sometimes, many times, it's just overlooked. And that is something I have touched upon in my previous videos too, but I doubt whether I have made a full video dedicated just to this concept, and that's why I'm doing this right now. I hope that makes sense. So yes, the thing is that, what is a law of physics, or let's say a law of science? We say that every system must follow the laws of physics. This is a Newton's law of gravitation, this law of that. But what even is a law? So let's focus on the word law first of all. So when we say law or any legal kind of thing, that is a human construct, right? For the human society, humans have agreed on some common ground, and that no, this is something which is definitely unacceptable, so let's make it illegal. And that is something which is how it should be, so let's make it legal. And how to enforce this law? So this human society law is something we humans have constructed, right? Now, how is the law of science different? Why is it called law? Must be something in common, right? So what is the law of science? What do we mean by law of science? Is it something like some constitution written by God, and God handed it down to us? So okay, here is the constitution of science, so that these are the laws of science. You must follow the constitution, just like you must follow the laws of science. Obviously, it's not something like that. Scientists made the laws of science. Now, whether scientists discovered the laws of science, or whether they made it, or whether there's something more fundamental, that is the big thing, right? In mathematics, we talk about Platonism, whether mathematical truths are discovered or invented. So it's much the same thing, at least the same idea. So would you, like, let's say that the example I always like to start with. First of all, let me be very specific. I always try to, it might appear that I'm trying to mix physics and philosophy. No, I'm not. That's not what I'm trying to do. It's a very very common misconception that people have about me. By people, I mean the people who know me and my friends, my colleagues, and also the people who watch my YouTube videos. But maybe they don't know me personally. So I don't. I mean, I get it. I understand the way I speak, the way I write. Even in my rigorous papers, maybe there is an appendix which is a bit philosophical. I understand why people have this I don't know, like, why people have this kind of thought about me, this kind of notion about me. What should I call it? Why people feel this way about me, basically, that I'm trying to mix physics and philosophy. No, I'm not. And I don't think that's a good idea in the first place. See, there are two problems here, and it's kind of like a paradox, almost like a paradox, like a dilemma. The dilemma is that, at the end of the day, we are all humans. Even the most rigorous data scientist, like who works only with data, who has nothing else in his life other than data, or let's say the most rigorous physicist, whatever it is, or if it's someone like maybe an artist or a philosopher, like an actual philosopher by profession. But at the end of the day, we're all humans and we need something to, like, even the physicists, most of them must have chosen physics because at one point or other they have romanticized physics. They have I should say they have yeah, in a way they have romanticized the subject. They have found beauty in physics. They have found some purpose in physics. No, I love physics, so I have to do physics. There are a few people who come into physics because they are kind of forced into it. Okay, I have nothing better to do. I did not get accepted in that course, so let's do a course in physics. And then they are kind of trapped in the physics ecosystem, and they're just doing a PhD and stuff in physics just for the sake of it. It's possible. Doing a PhD in physics doesn't guarantee you are great. This is true because if you do a really good PhD, then that means you should have some real passion for the subject and some real knowledge, some real way of thinking. But if you just want to do an average PhD in physics, you don't need to be a like you don't need to learn how to think like a physicist. You don't need to see the subject for that. If you're just okay with a little bit of like training, formal training, not that doesn't prove that you are talented or something. You can more or less manage that in many places. Maybe not the top places, but in many places. So yeah, and the situation has changed a lot after this artificial intelligence, chat gpt and all, but let's not get into that in this video. So yeah, but the point I was trying to make is that most people need some reason for doing what they do, whether it's physics, doing physics for a physicist, doing music for a musician, doing even a routine corporate job for those professionals, whatever it is. So for them, if you cannot find meaning in job, maybe for them meaning is money. Okay, maybe I don't like my job, I don't find a lot of meaning in it, but at least I get a lot of money. I get paid very generously for my job, and I can use the money to enjoy my life as I want. So the meaning there lies in the money. But for true physicists, I think the meaning usually doesn't lie for the money they're getting. Usually physicists are not very well paid as compared to other job options, especially compared to the level, the depth, the rigor, the education, the effort they put into. Not really well paid on average. Now, still, I'm not complaining, and a true physicist should not complain because they're not in physics for the money. If they are, then that means they're not there. They have not seen the true beauty of the subject. That there is nothing wrong in it. Of course, it's just a profession. Just like you can be a corporate professional without loving it, you can be a physicist without loving physics. You can be a physicist. There is nothing wrong in that. But I'm just saying. So that means at one point it becomes important to romanticize the subject just to keep your interest alive. Because when you're maybe, let's say you're a high school student, and if you see physics just for what it is, just some formulas and some models, some approximations, I'm pretty sure you won't love physics. At high school level, we have a very different idea of physics. So physics is that, like, the genius or something, like the most fundamental science. I'll be solving Einstein's theory, I'll be solving wormholes, black holes, time travel, all those exotic stuff, quantum mechanics. And yeah, but then when you actually come into physics, you see that okay, this is still exciting, this is still it's actually very surprising why this all even works. How come some mathematical laws actually work so well in describing the real world? I don't know whether we should feel lucky that we have laws, or whether we should feel disturbed that we have laws that work at all. But again, that's a different question. So but once you come into physics, you will see that what we are doing is just like, in a way, just like routine job. We are just running simulations, like just like corporate people, they do some routine stuff. They attend to tickets, they do stuff like, I don't know, I don't exactly know what they do, but yeah, I have a basic idea. Talking to clients and attending client meetings, client calls and stuff. We are although it might appear like scientists are they have a bit more interesting career, although maybe not very well paid in that sense. But we do the same thing technically. We go to the lab daily, we follow some routine procedures, some protocols, we run simulations, and from time to time we try to think in a different way and try to see if that works out in reality. I mean, by checking with data, like data driven model simulations, or even sometimes by doing analytical calculations. But yeah, technically we are trained, the physics, and we try to sometimes have new ideas, but it's not what it seems like. We are having new ideas every other day. It's like a very, like, every day we go like, eureka, I got it. It's not like that. So in that sense, even research is a very boring, can become a very boring profession. It's true, any profession gets boring after a certain point. It's human nature. But that means to keep yourself motivated, it's important to inwardly fantasize, not really fantasize, but I should say romanticize your, it's in a way fantasy, because like sometimes I find myself fantasizing about physics, like, okay, what if I could find a connection between two very unique kind of connection between different branches of physics that nobody has dreamt of. And the fantasy for me is not because I would be like I would get a international recognition for this. Whether I get the recognition or not is secondary. I agree that is important. We cannot. I won't try to behave like that's not at all important. Some amount of recognition is important. It would ensure a more stable income, future grants, fundings. All that is important. Okay, uh, but yeah, if you really care about the question, you would only care about the answer and not who answered it. If you care about who answered it, no, must be the one to solve the problem to answer this question. That means you care about about getting credited for the discovery, which is important, but that should not be the most important thing if you really love the subject, in my opinion. But yeah, so but at the same time there is a very grave risk, very grave danger if you romanticize your field, especially if it's something like physics or science. In art it's a different story, I guess, but in science, if you romanticize physics and stuff, and then when you realize that actually it's not at all that romantic or that original or that interesting, it's just like routine, that can be a very big shock. And this is one of the dangers, but the even bigger problem with romanticizing physics or this kind of maybe data analysis mathematics is that you risk forming an internal bias, an unconscious bias about the subject if you keep romanticizing it without even realizing that you are actually forming a bias. And this is a very deep problem, because if you form a bias like this, it will affect all your thinking, your entire thought process, and even your research if you're trying to do some new kind of research, right? So because physics is not romantic, physics is not beautiful because it solves the questions, we don't know why. That is a very deep mysterious question, but that doesn't, we shouldn't start just romanticizing mystery just for the sake of that. We should try to find the answers. And physics is something we built models based on some empirical observations, some intuitions, which is something we have. Machines don't. Artificial intelligence, they don't have this intuition. Machines can only think like backward, like they have all the memory. By memory I mean the past, whatever data is there on the internet, but they cannot think forward. They cannot really anticipate about the future the way a human can. We can have daydreams, we can anticipate what I'm going to be after 5 years. This is something a machine cannot do. A machine can try to extrapolate data, it has some data, but it's very difficult. In most cases such predictions fail. I mean, if it's a real well defined model, maybe not, but in general in life, if you want to extrapolate based on the past what you will be in the future, definitely such predictions are going to fail. 2 years ago I was so much into quantum physics. If you told me that I will be doing biological physics, I would definitely not believe you, but here I am. 5 years ago I used to kind of hate physics. 6 years ago. So this kind of extrapolations never really work if it's based on entire artificial intelligence is just statistical knowledge. It's a very important distinction which people often forget, is between statistical knowledge and symbolic knowledge. So what the artificial intelligence does is that it gives you a statistical answer. If you ask it what is 2 plus 2, it tells you 2 plus 2 is 4. But it doesn't really calculate, really understand that and give you the analytical solution. Analytical solution, we can do analytically solve a problem. AI cannot. Even the reply the AI gives to a question, to a very simple question like what is 2 plus 2, even that is a statistical reply. The AI checks all the database and it sees that almost everywhere 2 plus 2 is 4, so that's why it gives you the answer without even understanding why 2 plus 2 is 4. So that is called statistical knowledge, guessing basically, not symbolic knowledge. So anyway, so there is a problem about, you should at some point you should think about your field as something more than a routine field of inquiry, otherwise you will lose your interest. So in that sense, maybe inwardly romanticizing physics is a good practice, but at the same time you should keep in mind the limits. It should not, that romanticism shouldn't get out of hand, that you start thinking science fiction instead of science. But at the same time, yeah, like I told you, there are some difficulties, there are some problems about romanticizing physics as well, about the forming biases, and there's some very great problems, like serious problems, potential problems, right? And the next thing I wanted to discuss is that, so when I say what are the limits of physics, this is the main thing actually I want to discuss in the video. So what are laws of physics or of science? What do you mean by laws? Like, are they they're always work or something? What do I even mean by work? Like, do the laws actually describe the real system? This is even more important to ask. I think the answer is, and this is very important to realize, is that all of physics in a way is an attempt to model the real world, but not to describe the real world as it is, simply because it's impossible. I'm not questioning the method of physics. It's definitely a very successful method. There are some places which needs change, which will come along gradually, but I'm not questioning the method of physics. I don't have a better method myself, if I'm being very honest with you guys, but I'm saying that this is the only method that should work, true, but still important to keep in mind that this is still a model. We are modeling the real world. We are not. Law of physics doesn't describe the real world. It describes in the sense that, yeah, a model describes it simulates, it recreates the behavior of the real world under some assumptions. So in a way it maps it, but it not describes the behavior as it is, simply because we don't even know what the real world is. We are confined by our senses and all. So if I ask you, why does the apple fall down, and you give me the answer that it falls down because of Newton's law, no. The apple does not know, does not understand Newton's law of gravitation. The apple does not say, okay, so there is some law called Newton's law, so I am expected to follow the law, so let me fall down. No. If I think about, let's say, I don't know, if I think about, let's say, killing somebody, is a very, very, very bad example maybe, but yeah. So automatically I will think that, no, this is against the law, I am not supposed to do this is against the law, so I will not kill that person. Just a very rough example. But that's why it's a law. There is a law in the constitution that a murder is a punishable offense. But the apple doesn't do that, obviously. When the apple doesn't decide, okay, so I have a lot of ways to, I can either move up or move down, but according to Newton's law, there is a law which says that I should move down, so that's why let me fall. Of course not. So then why even does the apple fall? Newton's law only models the behavior of the apple, and like Newton's law, like most of the laws in physics, this law is kind of, it began empirically. Let Newton observed the behavior of bodies, and it's not just the apple and the earth, it's any two bodies in general. And he saw that, okay, if I just try to model it using this kind of equation where the force between, the attractive force between them is proportional to both their masses, and the force grows weaker over time, so that's why it should be inversely proportional to r. Now the inverse square law, the r squared, that was kind of, there's a story to it. Like Kepler already did some calculations, like in Kepler's model, and there were some, I think Kepler, and there were some previous models. So you may ask, why did Newton chose the, like empirically, okay, the heavier the body is, the more the attraction, so it's easy to say that the force will be proportional to m1 and m2 if m1 and m2 are the masses of the two bodies. But how did Newton know that? Because this law is not entirely derivable, so how did Newton know that this force should be inversely proportional to r squared? He could have chosen r cube or r. He could have simply chosen 1 by r or 1 by r cube. In general relativity, things are a bit more rigid, because in general relativity we have this geometric interpretation. So if you replace the r square with something else like r cube, the theory breaks down. So that means you can actually explain in general relativity why exactly we have a r square. In Newton's law, there is no direct answer to that why, but there are some reasons. Of course, there are some reasons. Newton didn't just assume the inverse square law. But anyway, so this law only models the behavior of this massive objects, these bodies, apple, earth, sun, moon, whatever it is. But it doesn't explain why does the apple fall down. So the reason I am telling this to you is that, in my opinion, a law is just a model of the world which models the behavior of the world at only one point in time. Because if you are being very rigorous, then if I talk about the whole time scale from the Big Bang, again we don't even know if Big Bang was indeed the beginning of time, or if it was like maybe something cyclic universe model, the universe is going through big bangs, like it was just a point in time. I mean, we don't even know whether time really began with Big Bang or what happened before the Big Bang. Anyway, but yeah, assuming Big Bang, the initial time t equals 0 corresponds to the Big Bang, then actually, if it's actually a law of science, I mean, if it's a very rigorous law, which is like a complete description, let's say complete description. The reason I say a law is not a complete description, because in my view, if I am to call it a complete description, then technically, the law should be able to, the law or the equation, whatever you have for whatever you're claiming to be the complete description, using that we should be able to model the behavior of the universe from the Big Bang to now. So everything in between, formation of galaxies, planets, life, trees, apples, everything. And then why at this moment the apple fell down, everything. Newton's law doesn't, I think no law in physics, no single law in physics does that. So it's just a rough model. So assuming the tree exists, assuming we're in this earth, assuming we're in this time frame, assuming the laws of physics, assuming the conditions are this, then the apple falls down. But where did even the apple come from? So if you want a complete answer, then technically that should also be part of your question, right? So no law does that, and that's why a law is only a model. It's not the full thing. This is a very good analogy, very good example, I think. You don't have, the apple falls down because the best answer we have today is that because it is the way the universe is. This behavior of apple falling down is in the best way to, is in synchronization with the way the universe evolves. Now why does the universe evolve that way? Is it because of, maybe can we model the falling of apple using some optimization principle, entropy? There are some new ideas about entropic gravity, or whether it's some general relativistic. We don't know. They are all models, and they have their pros and cons. They give a pretty accurate description, but none of them are the full model. I think we cannot have such a full description in a way. So yeah, that is the limit of physics I wanted to talk about in this video. And it's also a good idea to question yourself whenever you're thinking about physics, any physics concept, or maybe even any science concept. But especially this is relevant for the science or the physics, like the for the concepts that require math, that are heavily dependent on equations and mathematics, mainly equations. So it's good to ask yourself whether I can, because modeling, by modeling now by modeling I mean just running simulations and models. Like you have some equations and you just model it, you just simulate it. In today's world of AI, ChatGPT and all, the writing the code and getting the model is not the, like generating some impressive looking plots, some diagrams, some model, some output, basically some simulation. That is not the impressive part anymore. I mean, that's not the main thing. But drawing the right inferences, testing the limits of model, this is very important. And by this I mean, how can you understand whether you are there yet? Let's say you have a differential equation, which usually these models have like a complex nonlinear differential equations with maybe 3 or 4 terms. I don't know, like it's not very simple equation which you can analytically solve. If you can analytically solve it, there would be no need to simulate it using all this stuff. Yeah. So the question to ask yourself is that just look at the equation of your model. Don't code or simulate. Look at the simulations right now, not yet. Look at the equation and just ask yourself, okay, so what does this term do? A very good way to do it is that very standard practice, but still I'm saying this. Let's say you have 3 equations and you want to see what the first equation does to the time evolution. Let's say on the LHS you have some parameter x, you want to study the time evolution of x in your model. So you have dx dt is equal to, let's say you have 3 terms. They have different effects and all of them are important for the time evolution. But maybe under some limit you can ignore this term, under some other limit you can ignore that term. So the best way to do it is that, so first of all, you are interested in understanding what the first term does to the time evolution, so you ignore the other terms, just forget it. Not realistic in your model, but just assume just remove those 2 terms, and now this equation becomes a lot simpler. Definitely you just study it. Then you remove the first and the third terms and study the second term, and you do this. So basically, if you're at the level that even without plotting, if just by looking at the equation you can say that, okay, if I remove this term, my phase diagram would look like this, or maybe my this versus this plot would look like this instead of that. If you can do that just qualitatively, roughly, even without having to do the plots or the simulations, then you can understand that you have a very good idea of the model. So, and it's important to, this model building habit is very important. Just you are given a model, there are a lot of models, you are modifying it, doing simulation, that is the routine job. That is also very important, but still that is routine job. But building model, just I tell you some situation, some scenario, no matter however complex or however non-physics it may sound like. I must tell you something completely which has no relation to physics at all. You should always in the mind think of, okay, so let me just break it down. So what is changing? These are changing. So okay, they are the variables. On what parameters do they depend? Like there are something called order parameters, there are something called control parameters. So control parameters are the parameters you will tweak with hand. It could be, let's say, something like temperature for a thermodynamic system. An order parameter is something, the change of which you will study. You expect some interesting behavior if you change the order parameter. Maybe something like a phase transition, critical behavior. You understand? So first thing in your mind, okay, let me see if I can break this system into number of variables and parameters. Next thing, how to relate them. So should I study the time evolution of this variable? Okay, yes. Is it a good idea to model this in discrete steps, like for instance a Markov chain, like a discrete step, or maybe continuous time, like a differential equation, ddt, the time derivative? What would the terms look like? Okay, so you understand that this variable, it changes like this. So maybe there should be a term which decays exponentially, there should be a term which reinforces after a regular cycle. So maybe something like a sine or cos. This kind of, I'm just giving just an argument, nothing very rigorous, but this kind of thinking. And it's always important to explain to, that's why I say like pedagogically important. When I look at the, for instance, as part of my internships I have to look at a lot of research papers and stuff. Most papers skip the calculations, which I understand. The research papers are being written by experienced researchers and they're writing it for their colleagues, so they're assuming that the people who will be reading these papers already know the stuff. They won't assume that someone with no training, like maybe bachelor or master student, to be able to grasp all of this. But I think it's still a very good idea to, whenever looking at a research paper, maybe there is some calculation which is, of course, the entire analytical calculation is not shown, just the result is quoted and then you go to the simulations and stuff usually. But it's a good idea to try to derive analytically and what theorems of mathematics you need to use. Sometimes the derivation can be very long, so you should know when to give up, but it's always a good idea to try and derive it analytically and see the exact logic, how far you can go analytically, and when and when it stops, because usually you cannot solve the full system analytically. That's when you need to shift to numerical methods, numerical techniques, right? And But it's always a good idea to teach people something pedagogically. In a way, think about physics pedagogically, because like, ask yourself, okay, I'm studying this, I already know the backgrounds, but if I had to explain this to someone who doesn't understand even the basics, how to do that without equations maybe? And that this is very important. Now I would like to end the video by giving a very small example of what I mean by this. It might be a very stupid example, just came in my mind, but might also, just I would like to know your, as always, I'm open to comments, open to constructive criticism, open to comments, so feel free to comment. Yeah, so if suppose, let's say, a high school student who has no idea about entropy or arrow of time or like any cosmology, anything, just very very young student, he comes to you and asks you what is the arrow of time. Maybe let's say he has no formal idea about this, but maybe he has come across the term, or maybe he understands, he just, maybe somebody has told him that, the laws of physics would not change if time ran backward. Now to tell this to a high school student, it wouldn't make sense to them, I'm pretty sure. Laws of physics would also make sense, would also work if time ran backward. Okay, they would think about something like time travel or all those exotic time running backward thing that is common in like maybe some science fiction kind of thing. But what it really means is nothing very interesting or very like science fiction in a way. It just means that if you replace t with negative t in your equations, the physics remains the same. That is what we mean by time symmetry. Yeah, technically in principle, maybe, yeah, if time actually ran backward, we don't know what we mean by that. What parameters would change? Would entropy decrease? How do we even define time running backward? That's a deep question actually. Even what is time, we don't know. There is no general consensus. So yeah, and if such a person comes to you, very young high school student, and asks you to, okay, explain what is the arrow of time. I heard that in the microscopic level, at the quantum level, the physics would not change if I switched, like if time ran backward. Then in the real world, why can't we visit the past? Why is time always unidirectional? If I break a cup, why does the cup always break? Why does a broken cup cannot join? The very common examples. So basically, if the question that is being asked to you is, how can a bias, because this is like a bias, time is biased to run forward, to point to the future from the past, and not the other way around. So it's clearly a bias. So how can a bias emerge or arise from an unbiased system? Because initially at the microscopic level, everything was unbiased, right? We know that in quantum physics there is time symmetry. But when a lot of these particles are coming and forming a complex world, we see that somehow there is this, in the universe there is a bias, this arrow of time. So this arrow of time is not important I'm just trying to give a pedagogical example. This arrow of time is not important. But how to explain this situation, like how to create an imaginary situation or a scenario and explain to the student, like give him a very simple example of how bias can arise. And a very good way in my opinion, is to just the following example I'm about to give you. And I'm not sure if such an example exists in real academia. I've not checked, and I'm not sure if it actually makes sense physically. Maybe it doesn't. It's supposed to be just a toy example. So I think you can introduce bias by creating different rules in hierarchies. I mean, there can be some local rules, there can be some global rules, which is kind of obvious, but still I think the example will help. So let's say we have a system. Let's say we have a one-dimensional lattice, or if lattice would be a very complex word for a high school student, I understand. Let's say you have a straight road, and you are not allowed to move left or right or anywhere. You are only allowed to move either forward or backward, and a straight, small, narrow, but a straight road. Okay, so you can either move forward or move backward. Now you have equal probability of moving forward or backward. I think probability is something that will make sense to a student, even a high school student, like the basic, like not advanced, just. So you have a probability of 1/2 of moving, just like if you toss a coin, you have a probability half of getting head and a half probability of getting tail. So you have a half probability of moving forward or a half probability of moving backward. Let's say you toss a coin, if it's head you go forward, and if it's tail you go backward. So you can just directly link it to the coin toss experiment to make it even more relatable to the high school student, right? So now this is the local rule. Locally at your level, this is the rule that you are allowed to move both only forward and backward, but both with equal probabilities. This is a local rule. So right now this is symmetry. If you think about the road as time, so you can move forward and backward in time. But now let's say I add a global rule. Now this is a rule which does not operate always. The local rule always true. No matter where you are, at what time you are within the system, at what point you are, this rule will always be true, that you are allowed to move only forward and backward with probability 1/2 each, and you are not allowed to move any other direction. This rule applies locally to a particle or to let's say to the system, to the human. Let's say if it's a human on a road, but this rule is always true. But now let's say we introduce, in addition, we introduce a global rule which will not always be applicable, but it will be applicable in some situations, which is that if you move forward for 10 consecutive steps, which is very rare but not impossible, right? If you toss a coin, you can get head 10 times. You toss a coin 10 times, you get head, just a row of heads, 10 heads. Then maybe on the 11th throw, maybe you get a tail if you're lucky enough, or if you're not stuck on head. Now this global rule says that if you move in the same direction without going back once in between for 10 consecutive steps, could be forward or backward, then for the next 10 consecutive steps you are fixed in that direction. So that it's a global, it's not really a global rule actually. I'm using the term wrong. Global rule is not maybe the not best way to put it, but it's a rule that is not a general rule. I mean, that it's a general rule, but this rule will come into play only under a certain condition. Only if you have moved in the same direction for 10 steps consecutively in either of the two directions. Only then this, otherwise this rule still exists, it still holds, but it will have no effect on the system. But this is a way to introduce bias in the system, because still locally, fundamentally the rule that holds, that's still symmetric. You have a probability 1/2 of going this way or that way. That is still symmetric. That rule is still true. We have not changed that rule. But if I just add this condition that if you have done this for 10, this condition, then you will get a bias. Because for instance, you're just doing randomly, what happens? If you toss a coin, you will get head, tail, head, tail, like a random sequence. That's what happens. You're just doing this forward, backward, forward, backward. You're just doing this kind of. Not symmetrically maybe, but you're still more or less doing this. But by chance, for instance, let's say if you get consecutive like 10 steps forwards, then this rule will come into play. Then the local rule for that particular system, will not work. The local rule is still true. By the local rule, I mean this rule about you can go either forward or backward with probability 1/2. That rule is still true. But since you have gone 10 steps, and let's say we do this only for 10 steps. Like 8 steps and 9 steps is fine, doesn't matter. But once you hit 10 steps, then forget everything else. For the next 10 steps, you will be forced to move in the same direction. Now this is a way to introduce bias, because let's say if you move 10 steps into this direction, then you again move 10 steps into this direction. Now to again come back to the, let's say, to the mean position, you have to retrace 20 steps which in a go, which is very unrealistic, very less likely. It's possible, sure, but very less likely that you again retrace 20 steps. Because if you try, of course there will be retrace once you are out of this rule, you can again come back, but you come back sometimes, then again you will find a push in that direction. So we're introducing a bias towards the direction by this rule. You understand what? And this could, depending on how the system evolves, this could be either that or that. Or just to keep things interesting, we could say that okay, if that system goes 10 steps in the left direction, or let's say in the forward direction, it will have to go 10 more steps in the forward direction. But if it goes let's say 5 steps in the right direction, it goes 50 more steps in the right direction. That's a very clear bias, that there's a preference towards right, because it's more likely for us to go get 5 consecutive steps in the same direction than 10. And if you do that, then we move 50, but if you do 10, we move 10. Understand? That's an idea. So yeah, I think this was a good example to illustrate how you can explain these concepts without always referring to very technical terms or even equations or stuff. So anyway, I think I just discussed a very just in a random way. I discussed a lot of stuff at once. I don't know if it made sense, but definitely some points were important, and I would like to discuss with you further on this, because it's very important, very fundamental, and most of my viewers are, at least some of my viewers, at least, they're very interested in this kind of topics. They comment on my videos, and I learn a lot from these comments. Very informative, very long comments, and it really matters to me. Thank you that you take the time to write these comments, because I learn a lot, and hopefully other YouTube viewers who are looking at the comments, since YouTube is a public platform, hopefully they also get to learn, because they're those really very deep and insightful comments. So anyway, as always, I would like to know your comments, and thank you for watching.